for that introduction. Is everybody able to hear me? Great.
Yes.
Okay, yeah. So thank you for inviting me. I'd like to give a special thanks to Dr. Ganti Murthy for the invitation to participate here. And just to be part of this very esteemed group of scientists and researchers from all over the world is a really big privilege for me. I really want to just take this opportunity to share my experiences in commercialization and product development for cyber-physical systems. Now, we're calling it cyber-physical systems today. A few years ago, it was called, and I mean, it is still called Internet of Things. And then even going further back, it was machine-to-machine communication. So I've been part of this journey for quite a while now. And as my introduction said, I've had experience, building products and taking them to market. So I just want to have a very, let's say, casual conversation sharing some of these experiences, because a lot of the amazing research and new products and new solutions and new processes and that are being developed all over the world today in cyber-physical systems, the tech is just one aspect of it, right? When you take this to market, there are certain things that you need to start thinking about, which can also influence the technology itself that you choose to develop. So I just have a quick agenda. We talk about cyber-physical systems and digital transformation. Then we talk about the state of Indian agriculture and digital transformation and the digital transformation that is happening today, and the role cyber-physical systems have to play in that. And then lastly, we'll end with a research experiment that me and my team are working on right now, where we're doing IoT-enabled precision farming for Grand 9 banana here in Karnataka. So cyber-physical systems and digital transformation. Hold on, let me see if I can minimize this. Okay, yeah, there you go. So why do I bring up this concept of digital transformation? I mean, because I think there are a lot of lessons that can be learned that have happened over the last 20, 30 years, which are very applicable to cyber-physical systems today. And digital transformation has been around longer than cyber-physical systems. Digital transformation, ever since the advent of the personal computer, has really changed the way we do business, changed our personal lives. And there are a lot of lessons that can be learned from things like that, or the adoption of technology and the incorporation of that technology, those sort of technology into our daily life, which have the same, which cyber-physical systems have the same journey today. So let's talk about this digital transformation pyramid. Right. Most digital transformation, whether it is for an individual, for an organization, for a business, really has an impact in three different places. Right. It is successful commercialization of digital transformation technology, and similarly cyber-physical systems means it has to impact one of these three areas in this digital transformation pyramid, right? So we can start with the operations. And this is where most of the cyber-physical systems today try to target, make things more efficient. Take manual tasks, make them automated, or make automated tasks even easier to monitor. But it's really around this operational efficiency place, right? But there are two other areas which cyber-physical systems and digital transformation have a big part to play for any sort of business or any individual. It is at the strategy level, either in the business strategy or the product strategy, as well as the go-to-market strategy of that organization or business. So let me just bring that concept and make it a little bit more tangible. It's really, so for example, my first job was at a smart buildings company in the US. This was back in 2010. And it was bringing IoT to buildings. The whole idea was to make facilities management and building operations more efficient, right? So our customer at that point of time were facilities management companies. These were the companies that were tasked with maintaining these very large commercial real estate infrastructure. So there was a lot of work that goes into making sure your chillers, your heaters, your valves, your fans, the temperature set points in the building, all of that was optimized, right? So for a facilities management company, what are some of the things that fall under this business strategy category, right? For a facilities management company, occupant comfort is number one, right? Then reduce costs, right? So these are two of the things that can fall under the business strategy triangle. Then you come into the operations, right? It's identifying faults, it's identifying inefficiencies, it's ordering the new parts, it's doing the actual maintenance of the mechanical systems. That all comes under operations. And then what is a go-to-market strategy for a facilities management company? That is, okay, I need to be able to get more facilities to manage. I want to be able to get more clients and get their real estate portfolios under my management. So similarly, if we take the same concept of business strategy, of execution and go-to-market and bring it down to farmers, right? For farmers, what are some of the strategic objectives? It is to maximize profit, it's to lower the effort of cultivation, and to lower the risk of growing a crop. Right? Then you have the operations, which is the actual cultivation, planting, de-weeding, applying your inputs, irrigation, and such. And then finally, on the go-to-market side, what are the things that are important to the farmer on the go-to-market side? They want a good price for their product, and they want to make sure that they're able to sell it on time and easily. I mean, the buyer needs to be close to their farm in most cases, right? So no matter what sort of, let's say, organization or user that you are thinking about building a cyber-physical system for, it's very important to understand what their objectives are in these three different categories. And strategically, it's really good to think about addressing not just one, addressing two out of the three, right? And the reason why is because when you're introducing new technology to organizations or users that aren't familiar with it, there's oftentimes a learning curve, right? And so taking the example of smart buildings, right? Our core focus was increasing the operations and execution efficiency of facility management processes, right? So it's making sure that when faults are identified through these analytics, it's making sure that it's communicated to the facility manager. He's able to source his parts in time, and he's able to fix it in time, right? So it was really about optimizing the maintenance and then making sure that there is energy savings due to just more efficient operations of the building. So during the first few years of actually launching this product in the market, it took us a while to figure out how to do that, right? Like the technology of smart buildings was actually the easy part. It is figuring out how to apply the technology to create that value, right? And for the first few years, we actually didn't create a lot of value for the customers in the case of energy efficiency and operations. But a facility management company that had a smart buildings offering put them ahead of their competition in the go-to-market quadrant of this triangle, right? So because our technology allowed them to promote themselves as an advanced and forward-looking facilities management company, we actually ended up staying with them for these first 2 years when we were struggling to get these operational and energy savings. And because we helped them on the go-to-market, It gave us the time to be able to hone and fine-tune our product, and then finally we were able to deliver consistently and reliably good energy savings. So here is so it's really important to look at 2 out of the 3, right? So either you improve efficiency in operations and execution, you help business product strategy, business or product strategy decision making, or you help your users or your organizations or your customers increase their revenue. Lastly, I want to talk about the successful adoption of digital transformation technologies and similarly cyber-physical systems is less about the technology, but more about the mindset transformation. I mean, if we try to define digital transformation, it can be thought of as a catch-all term for implementing 3 things. It's technology, it's talent, and processes to improve businesses and satisfy their customers. Right? So, but I want to come back to these 3 things. It is technology, talent, and processes. Technology alone doesn't mean much if the talent is not there to understand it, and the processes are not there in place to actually extract value out of it. So it really comes hand in hand with these 3 things come hand in hand with each other. One is the technology, the other one is the talent, and the other one is the process, right? And it's basically from because we still live in a world that humans primarily are primarily involved in running businesses and doing work. I mean, maybe someday we have a fully automated society, but we're not there yet. Right? So as long as humans are involved, user experiences become incredibly key for the adoption. You can have the most efficient, most amazing technology, but if you aren't able to create a impactful user experience, then the adoption is just not going to happen. So I just want to spend some time talking about this and giving everybody an idea of what user experiences used to be, what they are today, and where they're going in the future. So if we look at mechanical equipment that, let's say maybe 30 years ago, 40 years ago, right? We were on this end, this no access to people did not have access to the data inside these mechanical systems. All the sensing, computation, and control was done inside the machine. And you really needed to be an expert in mechanical systems and electrical systems to be able to go in and figure out what's going on. Right? Then the advent of digital, let's say, communication protocols started coming into play, where it wasn't just electrical signals and voltage. There are actually these protocols that were built, and users could then quote unquote plug into the equipment and extract the data themselves. Now this, you didn't need to be let's say a mechanical and an electrical engineer and an expert in that system to be able to access the data. They made it easier for sure by giving, let's say, by just developing the option to plug into the system and extract the data. But oftentimes you still needed to have the right plug. You needed to have the driver for the right protocol to be able to talk to the system. And then finally, after the data was extracted, you'd have to massage it, you'd have to do all the data engineering, and then you'd have to create the visualizations yourselves, right? So oftentimes within this data export phase, you'd still need to be trained. You'd still need to have some level of expertise with interacting with these systems. And this was actually in the interest of the manufacturers of these systems. Because every time you need to figure out what's going on, you will need to call them, and they charge you for the services. And it was good for their business model. But then what started happening is IoT started coming into, it started to make its way into being more commercially viable, more affordable. The advent of cloud computing started to come into play, and it was driven by consumer demand that users wanted to see what was happening in these systems, right? So you had a few OEMs that took the lead, and everybody else followed. And basically, what happened was these equipment manufacturers would sell you the equipment, and it would come out, and it would come with out-of-the-box reports, alerts, and dashboards, right? So this is something that we are also currently experiencing today with a lot of manufacturers of equipment, where when you buy something, for example, I mean, if I bought smart lights for my house, Philips, the manufacturer of the smart lights, would give me an app on my phone. That app on my phone would have a predefined dashboard and some controls, right? So it was all out of the box. The manufacturer gave it to you. Now, what ended up happening there was that people started to get interested in all of the data that was available, right? And people started to want to create their own visualizations for their specific needs, right? So, for example, just going back to this the smart building space, right? For a facilities management company that was managing, let's say, the portfolio of a large bank, a global bank, they would have bank branches all over the world. They would want to be able to look at energy consumption grouped by region, or grouped by country, or grouped by regional manager, right? So they'd have different ways of, they'd have different needs for slicing and analyzing that data. What initially happened was these users would go back to these OEMs and say, yes, these reports are nice, but I want to see more. I want to see more. I want to see more. Now, these OEMs, wanting to keep their customers happy, started to create these, let's say, customer-specific reports. Problem is that every customer around the globe will have a different way that he's using the system, a different way of that he or she would like to analyze the data, to slice it, to visualize it. And it became basically too much for these OEMs to cater to. I mean, it is an impossible task. So they started to take the approach of self-service reporting, right? Where they'll give you your out-of-the-box dashboards, reports, and alerts, but they'll give you a platform, say, or a framework, let's say, to be able to create your own, right? Cloud providers today, like Amazon, Google, and Microsoft, they are big into this self-service reporting paradigm, and today it is quite the norm to be able to for a cyber-physical system, for it to come out with certain prepackaged reports, but then the user has to be able to configure their own. I mean, you're just not, because we want to create impactful user experiences, and there's no way that any OEM or any company making cyber-physical systems can think about all of the use cases and cater to everybody's needs. So self-service reporting became a big trend in the industry, and that is kind of where we are at today. We are at this intersection, I think, at the tail end of self-service reporting, and we are getting into contextual reporting. So here's where AI and machine learning come into building a very engaging user experience, right? So for example, going back to the facilities management experience, the global facilities manager will want to look at, let's say, what's happening in the buildings in the U.S. in the morning, and then they want to look at buildings in South Korea in the evening, because that is when it's morning for them, right? So your dashboard can automatically show you the U.S. analysis and data in the morning, and then when you log into the same dashboard in the evening, it'll show you what's happening in South Korea, right? It's all about presenting relevant information at the right time, where the user doesn't have to do everything self-serve, and part of that is handled by the AI and ML algorithms in the background. Okay. So now let's talk about what's happening in agriculture in India. And we've talked about a couple of key points when it comes to just in general, digital transformation and the adoption of cyber-physical systems. I just want to reiterate one more time: it is technology, it's talent, and its processes. So the current agri value chain in India has a lot of inefficiencies, and like I said, India is on this tier 1. It is mainly focused on operational efficiency today. And the majority of the activity, majority of the investment, the majority of the startups today within, let's say, agri-tech, basically are focused on two main areas. It's on the input side, so seeds, fertilizers, and it's on the outputs, right? And the way that has been digitized, cyber-physical systems don't have a part to play there, but it's mainly they've digitized it from making from a traditional approach of people and shops to e-commerce, right? So either so now you're able to buy your seeds and fertilizers via an app, or you can call a call center and place an order for those things and get the advisory you need. And then on the marketing side, you have these people that are trying to cut out the middlemen, and through that they basically use digital platforms to be able to manage and track the farmers, right? So it's basically e-commerce that has got the most traction in India today when it comes to the inputs and the outputs. And I just want to touch on how digital transformation and cyber-physical systems have a part to play in the rest of the value chain. So let's talk about loans and insurance. Loans and insurance, incredibly important part. It is one that is highly tied to politics in India today, and I guess globally. But the problem with loans and insurance is that the traditional risk assessment metrics don't really work for agriculture, right? Like us sitting here in the cities, we have a CIBIL score that is based on our financial history, and but farmers, oftentimes they aren't in the formal financial sector, and so they don't have a lot of financial history. But more importantly, it's the ability of a farmer to repay a loan or the risk of a successful crop has less to do with the actual farmer himself, but more to do with the environment, the stuff that is outside of the farmer's control. So there is major strides that are being taken today in being able to quantify environmental risk. Remote sensing has a very big part to play within this, looking at historically whether the farmer has planted his crop or not, whether the crop is done well or not. You can get a sense of those sorts of things through remote sensing. And then you have this idea of building crop models. They're these very complex mathematical equations which can simulate crop growth based on certain environmental conditions. Those sorts of crop models can aid in quantifying the environmental risk. So that's what's happening on the fintech, agriculture financial technology industry. Then you have the farming, your actual cultivation and harvesting. This is where precision agriculture, as we know it and are most familiar with it, happen. This is trying to maximize your yield and quality, minimize your inputs, and that has both an impact on the farmer himself and then the environment in general. Now moving on to the supply chain, when it comes to distribution and transport and storage, okay, traceability is a very big trend today in agriculture. So real-time tracking of, let's say, bags of produce through RFID tags, through QR codes, and environmental monitoring of the warehouses, environmental monitoring of the trucks, etc. Are the ways cyber-physical systems are making an impact today in the supply chain. Then when it comes to post-harvest processing and handling, the major trend here is quality assessment. Quality assessment through computer vision specifically is where there's a lot of innovation and advancement today. But computer vision, when it comes to quality assessment, will just show you what's on whether the fruit or whether the produce looks good, right? Whether it's a certain size, whether it has any blemishes, and then you can grade it into A grade, B grade, C grade produce. But where it's also heading is through spectral imaging. People are able, and I mean, take this with the caveat that every fruit is different, so the way this technology is applied, every fruit or vegetable is different, so the way this technology is applied changes and has its limitations when you go from crop to crop. But spectral imaging of fruits can give you, in certain cases, an idea of the sweetness and the nutritional content of the fruit or vegetable. So that's kind of what's happening across the value chain in India today. And I would say when it comes to cyber physical systems, we have the biggest opportunity within the farming and the supply chain side of it. If you consider remote sensing and to be part of cyber physical systems, which I do, then loans and insurance comes into play. But when it comes to the inputs and when it comes to selling, right now it's mainly e-commerce and that's how it's being digitized. So, like I said, we here at Digite, me and my team, we are focused on precision agriculture, so precision farming, so everything to do with minimizing the inputs to maximize the outputs. And within precision farming, there are three major groups of sensors. This slide may seem very trivial, but it kind of like sets the context and stage for my next few slides. And the one point that I want to make here is the commercial acceptance and trust within these large group of sensors. Environmental sensors today are are used commercially at scale, very widely accepted, very trusted. Soil sensors today, I would say, are second in that ranking, where the academic communities globally have a lot of faith and a lot of trust in them, and they are used a lot in research. But then when you go into actual commercial farming, it's starting. It's still in the early stages. Within India, within the US, Europe, and probably South Korea as well, I'd say the adoption is a lot higher than it is in India, but soil sensors are I'd say, ranked number 2. Ranked number 3 are plant sensors. Plant sensors today are extremely expensive, and the main problem with plant sensors are that plants actually come in very different shapes and sizes, right? So building one sensor to work across many different crops is hard, just because of I'll get to this a little bit later, but mainly it becomes a very complex thing of building a scalable sensor that will fit in many different crops. And because these plant sensors, again, it's still very early stages for them, they're just very, very expensive and cost prohibitive, basically, for agriculture today. So if you have to rank these, I'd say environmental sensors are highest in the commercial acceptance scale, then soil sensors, then plant sensors. So let's talk about soil sensors to start, right? And I just want to preface this by saying there are also soil pH and EC sensors, soil pH and soil electrical conductivity sensors. These are pretty standard today, and actually don't really have I'd say solid applications in cyber-physical systems, primarily because soil pH and EC is not something you need real-time control over and real-time monitoring over. It's something that you can do infrequently, maybe once or twice a year, and make whatever necessary adjustments you need to your soil by adding certain inputs, and then you're fine. It's not something that needs real-time monitoring and control. So when I talk about soil sensors, I'll talk about moisture sensors, and I'll talk about soil nutrient sensors. But I'm not forgetting about pH and EC, but they don't have, but the value for cyber-physical systems is not really there, in my opinion. So there are mainly two types of soil moisture sensors. There are volumetric water content sensors, and there are your soil water potential sensors. Now, what's the difference between the two? Volumetric water content sensors will give you a percentage of water content. So for every 100 grams of soil, you have 20 grams of water, right? So pretty simple, pretty easy to understand. Metric or water potential sensors look at the amount of force that is required to extract water from the soil, right? The drier the soil, the harder it is to extract water from it, and it in my opinion is a more direct correlation to the stress that the plant experiences at certain moisture levels in the soil. Just because the moisture level is a certain amount, it doesn't mean, well, depending on the soil texture, it may be easier or harder for the plant to extract it. So these metric or water potential sensors, in my opinion, have a more direct correlation to what we are trying to control. Basically, when you try to control irrigation, you're trying to control stress on the plant, right? You wanna make sure that the plant is not stressed in certain stages, and then in certain stages in the plant growth, you may want to put the plant into stress because then it'll increase the yield, right? So controlling the stress that the plant experiences is, in my opinion, a better way to go. I have this basic, let's say, chart here where you have cost on the x-axis and practicality on the y-axis. You can compare these sensors and many other factors like the complexity of the electrical circuit, its accuracy, its ease of deployment, how long it lasts in the field, like how often you have to replace these sensors, etc. There are many ways we can do it, but I just kind of grouped all of them into this one loose term called practicality. And between all of these different types of sensors, I feel that the granular matrix sensors, which are a form of this metric and water potential sensors, have the best ratio of practicality to cost. I'll just spend a few minutes talking about how these sensors work and what the difference is. And so let's start with resistance probes. These are the cheapest, like sub 100 rupee sensors. You can buy them at any hobby shop. These are highly inaccurate, very cheap, good for people that are learning electronics for the first time, but not suitable for research or not suitable for commercial use. Potentiometers are actually really good, but the problem is potentiometers themselves are not, you cannot connect them electronically. This is a sensor that works on physical properties of creating some suction and creating some pressure, and then being able to measure essentially the force that is required to suck water out of the soil. Really good, very accurate, but cannot be used for IoT or cyber-physical systems. Then you come into granular matrix, capacitance probes, and TDR probes. Capacitance probes and TDR probes, basically they are able to respond to soil moisture immediately, whereas your granular matrix sensors may take 2 to 3 hours to respond to changes in soil moisture. So if you want so if for whatever reason your research requires you to have very real-time readings of soil moisture, then you'd want to go for these capacitance and TDR probes. But for commercial agriculture, waiting 2 or 3 hours is not a big deal for a plant. Like for example, as a human, if I'm thirsty, if I drink water now, that's great. If I drink water 2 hours from now, it's also fine. It's not going to have a huge impact on my life, right? So 2 to 3 hours is okay for plants. The next thing to note is that capacitance probes and TDR probes, I've put them lower on the practicality scale, primarily because they need to be calibrated for every field. For every specific field, you need to calibrate these sensors to get accurate readings. Now, practically, so for research purposes, that is fine. Academic purposes, that is fine. Commercially, farmers are not going to be able to calibrate their own sensors. They have putting that expectation on them. It just doesn't work. So either as a company, you're going to have to go and do the calibration every single time, or you go for granular matrix sensors, which don't require as much calibration. They only require some calibration when you get into sandy soils. But for the majority of soil types, you don't need to do much calibration. The other thing to note is that these capacitance probes and TDR probes don't work well in high salinity soils. So if for whatever reason there's just been a lot of fertilizer being put over many years, your salinity will be high, or if the groundwater just has high salinity, then capacitance and TDR probes don't work very well. Granular matrix sensors, they actually work well, primarily because inside the granular matrix sensor, there is usually a gypsum capsule, and that gypsum capsule deteriorates over time, and that actually neutralizes the effects of salinity on the sensor itself. Neutron probes, I'm not going to pretend that I know how they work. I mean, I know that they use radioactive elements to be able to measure soil moisture. Highly impractical in the real world, extremely expensive. But I just wanted to put it on the chart to make sure that we are covering the full base. There are more types of soil moisture sensors out there, but these are, let's say, the major ones that are used today. Soil nutrient sensors. Real-time soil nutrient monitoring today, at least in my opinion, is a huge opportunity. There is not one commercially viable product that I've come across yet. If somebody else knows of one, please let me know. Like, you will be my hero. It would be really amazing. But the ability to basically optimize the fertilizer based on real-time readings of soil nutrients is a phenomenal concept. But like I said, just practically, it hasn't made its way to commercialization yet. Just to touch on what these two types of technologies that are used in soil nutrient sensors is, you have your optical sensors, which use spectroscopy, and then you have your electrochemical sensors, which are basically ion selective electrodes and different variations of ion selective electrodes. This would be really great. We aren't using this in our system today, but we would love to. And coming to environmental sensors, there are many different types of environmental sensors. Automatic weather stations are very standard products today. You have expensive ones, you have cheap ones. But for agriculture, these are the 5 parameters that you'd want to be looking at. 7 parameters actually, but temperature, humidity, barometric pressure, rainfall, wind speed, direction, and solar radiation. There are 2 things that you can do with this. The first is understand or be able to quantify the impact on plant growth based on adverse weather conditions, right? So build a relationship between the weather and your plant, right? So you can start building correlations and models for this. That's one thing. But the second thing, which is a more practical application, is microclimate weather forecasting. Weather forecast models today are only as good as the hyperlocal data that you have. And weather providers like IMD from our government and private weather companies all over the world, they will have weather stations that may or may not be close to where your field is. So having an automated weather station at your field allows you to use that data, put it into these, and augment the existing weather forecasts through pretty standard weather forecast models. It's not very complicated. Well, I mean, it is complicated to get it accurate, but there is a lot of research on how to use real-time information to do a weather forecast. So we've talked about soil sensors, we've talked about plant sensors, we've talked about environmental sensors. Now we get into plant sensors. Out of all of the plant sensors, there are two plant sensors that have made their way into commercial products. One is leaf wetness. So leaf wetness is not actually a sensor that you put on the plant. It is a sensor that looks like a leaf, it's kind of shaped like a leaf, and mimics the surface of a leaf. And the idea is, and it senses how wet a leaf would be within that area of your field. Leaf wetness is important because it helps in disease prediction. A combination of leaf wetness and weather parameters for certain crops, there have been disease prediction models that are out there, and yeah, it's using a combination of these microclimate and these automatic weather stations and leaf wetness sensors. The next thing that has made its way not as accepted as leaf wetness are canopy infrared thermometers. The basic idea is that the canopy temperature increases when your plant is under water stress. So you could use canopy temperature to be able to trigger and to schedule your irrigation. It's been looked at. There is some research out there. There are some commercial products out there, but it's not very, very widely used. Then you have your sensors, which are exclusively within the research field, which are your leaf psychrometers, stem psychrometers. Leaf psychrometer and stem psychrometer are a measure of leaf and stem water potential. Like earlier, we looked at that granular matrix sensor, which looks at soil water potential. Stem psychrometer does stem water potential. Leaf psychrometer does leaf water potential. I've heard of a couple of startups in the U.S. that are working on leaf water potential based irrigation scheduling, but they're still very early stage and probably still within their R&D phase. They haven't launched in the market yet. Sap flow sensors will give you an idea of not only the amount of water that's moving through the plant, but also you can have correlations with the nutrient uptake as well. So sap flow sensors do have applications in both irrigation and fertilization of the plants. As I said earlier, depending on the size of the plant, you'll have different types of sensors, different types of leaves, et cetera, et cetera. So it becomes kind of hard to be able to develop a one-size-fits-all. Optical analysis of crops has been around for even before digital technology. People have been looking at crops to see whether they're healthy and nutrient deficiencies, pest and disease. All of that was done visually. Computer vision to digitize that process. There's huge applications for that. But I just wanted to talk about the maybe non-obvious use of optical sensors, which is multispectral remote sensing, either by drones or by satellites. The idea is that healthy leaves reflect near infrared. So if you look at canopies through multispectral sensors, you'll be able to figure out which ones are healthy, which ones are not healthy. This is being used widely today by the government for yield estimation, for crop classification, and such. Okay, So this is the IoT system that we have made. The technology behind this is actually not the hard part. The hard part is application of this technology to improve yields and reduce the costs. I mean, the application of an IoT system for precision agriculture has to do with everything from the position of the sensors to how the sensors behave in different soil types, to understanding how to apply fertigation based on the different stresses in the plant. It's really about creating a package of practice which incorporates this sort of technology. That's the hard part. The technology itself is pretty standardized today, but basically we have one node which does soil moisture monitoring, one node that does monitoring plus control, and then one node which does control only. So we're able to control different zones within a field through the solenoid valves, and then we're able to control the main pump as well. All of the control is done at the edge. It's not done in the cloud, so that because of connectivity problems being a real concern in rural areas, we wanted to make sure that all of the logic, all of the control happens at the edge. And one of the key parts or interesting parts, I think, from the technology of the system is we used LoRa as the IoT protocol. And LoRa was built for one-way communication, but we're actually able to do both reading of sensors and control over the same LoRa network. So that was, I think, a little bit of innovation there. Here are pictures of these granular matrix sensors and how they look in the real world. We attach these granular matrix sensors to PVC pipes so that we can install them in the soil easily. We are doing a research experiment on the efficacy of automated irrigation and fertigation to optimize yield and quality of Gran 9 banana. We're doing this in collaboration with the National Research Center for Banana. Here is a picture of our experimental plot. We've taken it from a drone. We've done an RCPD approach where we have 3 replications of 3 irrigation treatments, 3 fertigation treatments. So we have 29 different zones. We have 12 trees per zone. 2 trees in each zone are monitored for soil moisture. Then we take the average of those 2 trees to trigger the irrigation for that zone. This is what it looks like from the top. Here is a picture earlier in the season. I chose this picture so that you can see the poles with the solar panels and the IoT nodes. So every pole is where we have a different sensor or a tree that is sensored. We have a total of 116 sensors in this half-acre plot. I do have a very short video of a drone, again, just flying through the field. So we are towards the end of this experiment, actually. We just got our first harvest. The results are very encouraging. We have been able to, and I mean, the experiment is not over. We haven't collected all of the data yet, but our preliminary results suggest that we've been able to get equivalent or more yield. How much more we're going to have to wait for the rest of the data to come in, but we've been able to get at least equivalent yield with 68% less water than the recommended irrigation schedule. 68%, that's a huge amount, I think. So the efficacy of these sorts of systems is there. I just want to end with a few thoughts and lessons learned from my experience in cyber-physical systems and digital transformation. Is one, identify the user for the product. Speak to the user, understand which tier of digital transformation they are in. Quantify the benefit and calculate the ROI. If you're trying to sell something, this becomes incredibly important. Keep in mind that adoption is less about technology and more about user experience. Coming back to that, it's tech, it's talent, and it's process, right? So this talent and process is something that needs to be front and center in everybody's focus. The last 2 are just general good tips for product development. Be relentless when it comes to listening to your users and make frequent updates to your product. That is it. So thank you so much for the opportunity. I know I may have ran a little bit long, but no, actually I'm on time. We have good 8 minutes for questions. So looking forward to hearing any questions from anybody.
Thank you very much, sir. We are honored to have with us Professor Ganti Murthy. I invite him to express his views. So please.
Yeah, thank you so much, Vasundhara. Thank you so much, Varun, for doing this. We really enjoyed your talk. And it was a great experience showing the actual kind of things that you're doing, and then the entire chain of how going all the way from the concepts to sensors to the field implementation, and then seeing how that actually relates to it. And then I have a few questions that basically I wanted to ask you, if that's okay. Vasundhara, do you want to ask questions, or how does that work? I don't know.
So it's whatever you feel comfortable, sir. Do you want me to?
Oh, okay. Yeah, I had one or two questions that I might want to ask.
Sure.
One is like the digital transformation pyramid that you were talking about, Professor Subramanian's one. That was very intriguing and very eye-opening, I would say. One thing I was thinking about as I was looking at that schematic was that when we look at Indian agriculture, so the entire value chain from all the way from the farmers to the big supply chain and consumers. So is it possible that we have each of our players, for example, the farmers are at a different level than the food supply logistics companies versus the actual some other consumers?
Hello. I lost you there. Not sure if it's me or. Are you able to hear me?
Professor Murthy, we are not able to hear you. Could you please check on your end?
Okay. I think I'll answer the question from what I understood. Basically, the question was: are different actors within the value chain at different stages of the digital transformation pyramid? And in theory, that can be the case. But in Indian agriculture today, and I'm not talking about global agriculture, I'm talking about Indian agriculture, everybody is within this tier one, the bottom of the pyramid. Everybody's looking at bringing more efficiency to current and existing processes. Before any industry starts getting into new ways of doing things, oftentimes you look at better ways of doing your existing jobs, right? And then you start looking at new ways of doing this, right? So, new things to do. Instead of looking at new things to do first, you look at optimizing things that you do currently. After that is fully optimized and you're happy and you're comfortable, and both the talent and the processes, so the understanding of the users is there and the processes are in place to extract as much value as possible, then you start looking at doing new things. I think there may be edge cases, and there are for sure outliers in any sort of analysis, but as a whole, I would say that anybody looking at cyber-physical systems for agriculture in India, focus on this tier one of the digital transformation pyramid.
Okay, sir. Sir, Professor Murthy has posted his questions in the chat box. I'll read that for you.
Sure.
If you could please answer. There is a trend for more detailed reports for the impactful user experience. How will the reports be used ultimately for making the change? Are we getting into a time of information overload?
Right. Information overload is a very real thing. My experience going back to smart buildings, for example, one of the first projects we had was for a Procter & Gamble research facility. This was a 2.5 million square feet building, very, very huge. And they had, I think, about 500 VAV pieces of equipment. A VAV box is basically, if you look at a single room, the air conditioning unit, like on that room in a central air conditioning system, is called a VAV box. So they had hundreds of those. What we first did was actually we created a visualization for every single one of the VAV boxes in that building. We realized that nobody has the time or the energy to be able to look at any of that, right? So this user experience journey of going from this basic reporting, right, where all of that information is there, to self-service reporting, where the user contextualizes that information to what they want, to then contextual reporting, which is taking away all of that information overload and only providing the user what they need at the time they need it, like relevant information at the right time. That is what contextual reporting is all about. Information overload is absolutely a concern. I believe that AI and ML have a big part to play in filtering out the majority of the data.
Okay, sir. Another question from his end is, how much of the sensing do we actually need? Especially in the context of soil and plant sensors, can we not use advanced modeling techniques for proxy for sensor? Ultimately, it is about getting a good estimate for the crop growth.
Absolutely. It depends on who the user is, right? Remote sensing and crop modeling have very good applications when you're looking at larger areas and when you're trying to make decisions, right? But at a farm level, those sorts of technologies have a limit. Well, they start losing accuracy as compared to actual sensors that you can put on the ground, right? So if you have an actual soil moisture sensor, it'll give you a way more accurate estimate of soil moisture that you can get from any model or remote sensing. And for on the ground, you need real-time soil moisture to do irrigation scheduling, right? But irrigation scheduling is not a concern for a decision maker at a government level, right? So depending on the user type, certain technologies have better applicability.
All right, sir. One more question. There is some effort on automating the tensiometers. What are your thoughts about that?
Yeah, I mean, if it can be done reliably, and then I'm all for it. I mean, these granular matrix sensors are essentially a proxy for tensiometers. Tensiometers are more accurate, so if you can automate and digitize a tensiometer and come out with a product that is cheaper than the granular matrix sensors. It has to be more cost effective for it to be commercially viable. But if it can be done at a more cost effective price, then I would choose a tensiometer over a granular matrix sensor.
Thank you, sir. These were all the questions from Professor Murthy's end. I hope you might be satisfied with your answers. Attendees may unmute themselves if they want to ask any questions. Meanwhile, I'll read out the next questions that we have. So the next question is from Mr. Chamkat, if that is what it is pronounced. Are there sensors available to detect plant diseases from leaf volatiles?
Not that I have come across, and basically the sensors that I do my research on are the ones that have made their way into commercial production. There might be something along these lines happening in the academic and research field, but no, I haven't come across that yet.
Okay, so next question is from Mr. Ravindra Yadav. He asks if he can get the chance to read your research and understand the mathematical concept behind the research. How can he access that?
Yeah, so we haven't finished our experiment yet. Our harvesting will continue through September and October, because certain zones where we put more stress on the plants have a delay in flowering and delay in harvesting. So as soon as it's done, it'll be published. My information, my contact information is here. I'll put it up on the slide. And please contact me, send me an email, and I'll get back to you as soon as we have something published.
Yeah, thank you, sir. We have another question from Mr. Gupta. How often you need to change the sensor that you have deployed in the field?
Very good question. So these granular matrix sensors are a little bit of a tricky sensor. Now, I want to talk about two things. One is reinstallation, and the second one is replacement of the sensor. So reinstallation, so basically these granular matrix sensors need to have very high connection to the soil, right? And thing is, over time, with the wetting and drying of the soil plus root growth of the plant, oftentimes these sensors can, or the gap between the soil and the sensor can expand to a point where it isn't connected, right? So when it comes to reinstallation of sensors, this happens, well, I wouldn't say quite often, because we have 29 zones. There were some zones that were more prone to us going and reinstalling the sensors. I'd say that within this, let's say 1.5 years that we've had the system live in the field, for a specific zone, maximum times of reinstallation will probably be 5 times over the year, or over the 18 months. But there are sensors that we haven't had to reinstall at all. When it comes to replacement of these sensors, the granular matrix sensors have a reported life of 2 years from the manufacturer. Your water content sensors have a longer life from the manufacturer. This is primarily because of the gypsum block in the granular matrix sensor dissolving over time. So rule of thumb, I mean, you don't want that sensor in your field for more than 2 years to be safe. Yeah, so we'd say, I mean, we've had to replace, I'd say, maybe 5% of the total number of sensors that we have installed, just because they've had some problem, they weren't reading properly, etc. And after many reinstallations, we still couldn't get good readings from the sensors. So about 5%, I'd say we've had to replace. Reinstallation, yeah, I mean, that sort of thing happens. The one thing that I would say is when developing an IoT system, make sure to have algorithms that look at the behavior of the sensor. Like if your sensor suddenly spikes, you want to be notified about that immediately. So don't overlook that part in the development. Use AI and ML to understand trends of sensors, and then when those sensors start behaving outside of those trends, then you need an alert immediately. Then either you go reinstall or replace the sensor.
Thank you, sir. I hope that answers the question. We also have with us Professor Vimal Bhatia from IIT Indore. So would you like to interact? So he has posted his question in the chat box. He says that they have developed an optics and ML-based technique for seed viability and charcoal rot diseases. Would it be possible to discuss sometimes next week?
Absolutely, absolutely. Yes, my contact information was just on the screen. And yes, please contact me, and I'd love to have a conversation.
So thank you very much, sir. Do we have any more questions from the audience end?
I think I'm back again. This is Digite. Thank you so much again, Varun, and thank you so much, Vasundhara. I just wanted to thank you both, and thank you so much. Thank you.
Yes, thank you so much for the opportunity. It was truly, truly great. I love the questions that were asked, and I hope to interact with anybody who'd like to take the conversation forward. in the future. So thank you very much.
Thank you, Professor Murthy. Sir, I don't think we have any more questions as of now, but sure, because you have shared all your contact details, people will contact you over email as well as your phone for further details.
Yes.
So, on the behalf of Indo-South Korea JNC, I would really like to thank you for sharing some wonderful insights on digital transformation of agricultural systems. You have walked us through different kind of sensors and their related aspects in too much depth, and I am really thankful to you for joining us, sir. Thank you very much.
Okay, thank you. Thank you. Thank you very much.